Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is detonate the maximum bombs. So let's go to LeetCode and give this problem a read. So you are given a list of bombs. The range of a bomb is defined as the area where its effect can be felt. This area is in the shape of a circle with the center as the location of the bomb. The bombs are represented by a zero indexed 2D integer array called bombs, where bombs at the ith position, this value has three values, which is xi, yi, and ri. X, y are the coordinates, and r is the basically the radius of that particular bomb. Now, you may choose to detonate a single bomb. When a bomb is detonated, it will detonate all other bombs that lie in its range. What is the range? Basically, that range would be from this particular bomb's radius. If the other bombs are in that radius, then basically their center, which is their coordinate, is in that range. Then that will also detonate. Given the list of bombs, return the maximum number of bombs that can be detonated if you are allowed to detonate only one bomb. So detonate the maximum bombs. This problem is marked medium on LeetCode. Here in our input, we are given this list of bombs where each ith position has basically the bomb's location. These are the two coordinates, and then this is the radius of the bomb. So if you see the first bomb or 0th bomb in this case, because index starts at 0, this one right here, it's 1 and 2, so 1 right here and then 2 right here, right? This is y and this is x. So this is the first bomb, 0th bomb. Now this one has the radius of 3, and we only need to choose one bomb to detonate. And here, if let's say we choose this 0th bomb, then there are two bombs in its radius, in its range. So this is the range, this is the r radius, which is 3. So if you see the bomb 1 and bomb 2, they both lie in its radius. So these two bombs, this one and this one, they will also detonate. So this second bomb, so first radius is just 1, so let's ignore that. But second, because it's also getting detonated when you detonate 0th bomb, then you see that bomb 3, which is this, its radius is also in its second bomb's radius, range or radius, whatever you want to say. And then when you detonate this third one, its radius is quite huge, which is also 3, and this one basically detonates the fourth bomb. So there are 5 bombs, so 0, 1, 2, 3, 4. These all get detonated when you detonate this 0th bomb. So basically what I'm saying is these all bombs, they do lie on, they are basically connected component. So they're all connected as one in terms of they're all indirectly connected. That is what I'm trying to say. And we are going to solve this problem using graph traversal, where we will treat each bomb as a node of the graph. And here we will basically be calculating if a bomb is connected to other bombs and those other bombs are connected to other bombs. And we are going to choose basically the maximum size component, connected component from this entire graph. So here you see all of these are connected. But maybe there was one more value, one more bomb, but it was maybe lying somewhere here and its radius was just like this. Then it will remain itself like disconnected component from this main bigger component. But at the end of the day, this is a part of the big bomb group or graph. So we are going to treat all these bombs as the node of a graph such that we connect them in a way when you detonate like any of these bombs, the other bombs basically become the neighbors. So from this one right here, if this one detonates, these two become the neighbor of this first bomb. So this has to be a directed graph, right? This has to be a directed graph, because detonating detonating first one, this 0th one, basically also explodes first and this first and two, but if you see, detonating this 2 does not detonate 0th bomb because its range is only right here. All right, so this, its neighbor would be 1, but 1's range is not even like, you know, reachable to 2, or it is reachable. I think it is just this much, but we'll just calculate and create our graph adjacency list, which will basically give us a directed graph. But remember, at the end of the day, we are returning the maximum size of this connected component. So you know, the largest connected component we are returning, and its size basically. So here we will create this adjacency graph. So I will basically have, let's say I'm gonna call it graph, and I'm just gonna use the green color here, and I will actually do its size. So graph here will be directed graph, and we are going to basically create this graph by traversing all these values, and you'll see how you connect these, because at the end of the day, for calculating what are the other nodes in the range of first bomb or node, whatever you guys want to call it, we will calculate its distance to other components. So we will be basically using 2 for loops to get to, you know, so that we can actually calculate if the distance to these actually lies in the range that it has, which is the radius of the first one. So here what we'll be doing is actually we'll be using 2 for loops. So for I in range, and I'm gonna call n is the number of nodes, and for j in range, also n, and if I equals to j, then continue. Otherwise you're going to basically have this xi, yi, and ri, getting it from basically the bombs at the ith value, and you'll do the same thing, but for the jth. So right here, it's just like that. You will calculate it for j, and then this will also be j. Now you want to calculate that distance. So let's calculate that distance. Distance is going to be under root xi minus xj square plus yi minus yj square. This will give me the distance, and if this distance is actually less than or equals to ri, then j will become a neighbor of ri, or that particular bomb. So I will add this to my graph. So graph I dot append this j. So j is the neighbor. So that means j is reachable from ith bomb. So what we are going to do now is this is all of the code that we will need to basically create our graph. All right, this is the node this is the code, sorry, not the node. This is the code, entire code we will be basically using to create our graph. So I'm just gonna get rid of this and move this code right here. All right, now let me just write the values of the graph for this example that will be created. So I'll just call it graph. It will be for each, so 0, 1, 2, 3, and 4. These are the 5 bombs that we have. Let's basically have all these neighbors. So for 0th, it's connected to 1 and it's connected to 2. So we are not going to add 0 to itself, because 0 is detonating itself, right? We are choosing to detonate, so then all these neighbors will also be detonated. Then for one bomb, first bomb, it will be in the range, you can check what will be the other nodes in the range of first bomb. So this is going to be actually I think it can take 0. Can it take a 0? We'll have to calculate the distance. So for this one right here, what are the bombs going to be in this range? Well, that doesn't matter. I don't want to do it like this, but I will just take an example from here. So for second one, it's 1, 1 and 2. I don't want to get into too much detail, and that is for 2 and 2. For 3, it's going to be this is the third bomb. So for this, the radius is 3, and it's going to be 4, etc., etc. Yeah, I mean, you can calculate and do it. I'm just not trying to waste my time over this. Now, once we have this, I'm just gonna write exit etc. All right. So this is not completely done, but that's not the the core of. This is the code that you will need to create the graph. This will give you the graph. But what are we going to do is, now the next step is find max size connected component from this graph. Isn't that what we need? Yes, we do, right? So we will write best algorithm here would be a BFS, because it travels faster than DFS, because DFS goes to just one child node and then child nodes, neighbors, and their neighbors, and then come back. But here what we are really trying to do is just spread all our wings and just find all the connected nodes. We are not doing any operation with those. We're just trying to find how many nodes are connected with other nodes. All right, so here we will use BFS. Now BFS will be taking basically a node and then a visited set. So visited set, because this will be independent to the node we are running the BFS at, and then return size of all nodes in the nodes reach. I'm not writing the pseudocode for BFS. We have done it like thousands of times. That is it. For time complexity, we can say that when we are traversing this n, we are basically going through each n and we are comparing it with the other n nodes. So it's going to be n square. Also BFS will also be we are running it for n number of nodes, so that will also be I would say, if all are separated and BFS itself take n time complexity, it's also going to be n square. For space complexity, we are storing it in just visited set or graph, so that will be the size of I'll say that will be the size of n. And yes, let's go implement this solution. It will be quite straightforward, although this problem is marked medium, but I guess if you approach it really nicely, with intuition, then and it's a really nicely designed problem. And I think Google asked this. Google is always known for asking very intuitive questions to find its best engineers. Okay, so we're gonna create graph. Initially, it's going to be a default dict list. Okay, default dict, and then let's fill this up. And before we dive in, I'm just gonna calculate the size of this bombs. Okay, let's go over for I in range n. So for each bomb, we are comparing with another bombs, and then not comparing, but basically trying to find that distance between them so that we can append the second one to first neighbors. So for j in range, also n, and we don't want to like deal when I is equal to j. So if I is the same bomb, then of course it's gonna detonate itself. So we just continue. We don't have to add it to. So we are not doing these self edges, right? That's the better way of saying it. All right. So otherwise, let's unfold all these values. So xi, ji, and ri. So this will give me from bombs ith node or ith bomb, and then let's get it from the jth position. That is it. Okay, now let's calculate the distance. Distance would be sqrt and then xi minus xj 2 plus yi minus yj and 2, and then that is it. That will give me the distance. This is sqrt, x distance, y distance, and then you square both of them, combine them, and take the sqrt. So if this distance less than equals to the radius for I, so ri, then I can append to my graph. So graph at basically ith bomb's neighbors will be append this j. That is it. We have created the graph right now. Let's declare the BFS right here, which will be taking node and visited set. But before we do that, I'm gonna just write pass and do the main work here. So let's have count that we will be returning, or not count, we can just call it answer, and for node in range n, and I'm just gonna update my answer by answer will be the maximum from these connected max size of largest connected component. So size of these components, these connected components, I mean. So here it will be maximum of either the answer that I've already found or whatever BFS returns when I provided the node, and it will bring the size of all the nodes reachable from this node. Now it will also take the visited set. I'm just gonna send it an empty set, right? And then finally I will return answer. So you can see all the code right here, and now we will implement BFS. So for BFS, we have a DQ, more efficient, and here I will be adding a node to my DQ, this node to my DQ, then to visited set I will add it. So add this node, and at the same time I want to actually start my count with 1, because at the end of the day I am trying to count the number of nodes in this whole network of this node, all the nodes reachable from node. So I'm already starting with 1 value, because node is the count, it makes the count 1. Let's shift this a little up. So it's the while loop that we work with. So while q is not empty, let's get the first u node from q. So q dot pop left, and here I will now try to explore all the neighbors of in the graph of u, and if this neighbor not in visited, then I will add it to my queue, or append, it's a better word, append to my queue's neighbor, but at the same time I am visiting it, so I'll add it to my visit set as well. So there you go. And I think that would be it. But one more thing, because I'm exploring a connected neighbor, then I will increment my count as well right here by 1, and then I will return this count. So I'll zoom out so that we can see the entire code, all of it together. This is the entire code for maximum detonation. We have the graph as a list. We went through basically all the bombs and all the bombs that could be potential neighbors of ith bomb, and then we added to the graphs list, the neighbors list, after calculating the distance, which lies in the range of ith bomb's radius. And then we have the we go node by node and then calculate our answer by basically maximizing it, either itself like 0 or whatever BFS returns, and this BFS will return you the size of the each connected component. So there you go. This is the entire code. This is a regular BFS. I've added just extra one line for count, and this count will be incremented each time it finds a new neighbor for the node that we just sent it. So that is it. Let's try to run this. I hope there is no typo. And there is, and that is because for neighbor in, off is the language of JavaScript, not this. Did I say JavaScript? Okay, what did I do? So of course this is y. Sorry, this is RG. I think now everything should be good. Oh my god. XI, YI, RI. XI minus XJ, YI minus YJ. And RI. Stupid me, I am sorry. Well, now it's done. Submitted. I mean, these typos happen all the time. Okay, let's write down the time complexity. It will be, as we talked about, n square, not n at the rate, and space complexity will be big of n. Is it also n square? Because we are creating this graph is storing n number of nodes, but also the edges, so it's going to be v plus e. But at the same time, we're not doing anything else in terms of this space complexity, so v plus e. And this you can just say v square. Yeah, makes it simple to understand. Let's go back to AlgoYogi, mark this solved. See you guys later in the next problem. So there were a lot of problem in graph, and we are getting close to wrapping all of them up. We have a couple of medium left. So 1, 2, 3, 4, 5 medium left. And then we have like 6 hard. And then we'll be done, and we'll be moving to our final topic, dynamic programming. And before that, I will be adding another section right here for system design, and in the front page I'll be adding like a my calendar, like to do if you want to do a mock interview with me, or you want to you want me to do a mock interview of you, or pair programming, or like you want to talk to me about anything, everything. I live in New York City, whatsoever. I don't know what the fuck I'm saying. Well, anyway, I think I just it's easy for me to talk about certain ideas that I have, and then work over them rather than just not talk about it and never do it.